About XQuery and static typing.
So, hi. So the reason I'll talk about XQuery is because so it is a language which is supposed to feature static typing, but some expressions in the language have resisted typing. So I'll start by explaining what the problem we try to solve is. So in XQuery, so in a simplified version of XQuery, values are sequences of tree nodes which can come from different trees or the same tree, possibly. So here S is an example of an XQuery value. So we have two C nodes which actually come from the same tree, and then an X node from another tree. So that's an XQuery value. So you don't write a literal value like this. So the way you obtain such a value is by applying some requests on documents. So you always start from documents which are trees. And you can write, for example, so I have two documents, D1 and D2, these two trees here. And I want to select all C nodes which are descendants of my first node, here A, and all grandchildren of my second document. So I obtained the value S above. So then when I have this S, what can I do with it? So I can do several things. So for example, I can construct a new tree. So I can decide to put S in a K, under a K. And so what it does is it extracts all subtrees and puts them under a K node here. So we have extracted the three subtrees corresponding to the two C's and the X, and have a K. But I can also do other things with my sequence. So I can navigate from the nodes in it in any direction. So for example, I can decide I want to select all the following siblings of all the nodes in my sequence. So here, the following sibling, the next sibling of the first C is a D node, and the other elements in my sequence have no following siblings. So I get a singleton sequence with just one D, which is the third child of the A. And then, after this operation, I can again put it in a new tree. So for example, I will put a Z on top of it. So that's a small extract of what you can do with XQuery. And then you want to type that. So what you have is a set of type constraints which take the form of regular tree types. And so I'll take the example of DTD, which is simpler. So in DTD, the type of a node is determined by its label. So each label is associated to a regular expression of children, which represents all the sequences of children which are allowed for a node with this label. So here, for example, here's type information for my input. And so here, for example, each A node is supposed to have a sequence that of children which matches BCD star. And I also have type information for the trees I'm trying to build. So here, K and Z in my examples. Then my sequences of nodes, well, in the classical system, what I will do is the sequence of nodes has a type which is a regular expression of node types. So here, I can compute that S has type C star X question. And if I want to type my first example expression, well, it's okay. K expects a sequence of children of the form C star X question, and that's what I have, so okay. But if I want to type my second expression, I have got a problem because My type is C star X question, and I want to know if I will obtain A question, B or C or D star by applying following sibling to it. And, well, I can't do that. So the problem we have is that our type language is regular tree types, which describe trees. But the language manipulates nodes and can navigate in any direction from them. So the type language does not contain enough information. So one thing we can do is enrich this language, and one thing we can enrich it with is modal logic. So with modal logic, it is easy to build a modal logic which allows navigating any direction in a binary tree. So we have these things called modalities. So one means first child, two second child. The diamond is the existential, the other is universal. So for example, diamond 1 phi means I have a first child and it satisfies phi. Square 1 means if I have a first child, it satisfies phi. And I can also navigate backwards with the converse modalities. So it works in binary trees. Here we have n-array trees, but it also works because the nodes are ordered, and so we can represent such an n-array tree as a binary tree by using first child, next sibling as the two modalities. And then if we add recursion to this logic language, we can easily express properties such as one of my ancestors satisfies some formula phi, etc. So if we have this language, well, we can translate regular tree types into formulas. So here, this is the type information I have, and I will translate it into a set of mutually recursive formulas. So here, for example, A means I have a label A, and if I have a first child, then it satisfies the regular formula, which says I am B. I have a sibling which satisfies C, etc. So we can translate these types. So we will have types phi1, formulas phi1 and phi2 describing our two input documents. And then to type our sequence, we can compute a regular expression of formulas. So using formulas such as ancestor of phi1, so I don't detail what this formula is, but it's easy to write it using recursion on the backward modalities. So I can build this type for my sequence. And then if I apply following sibling to that sequence, I can again build a regular expression of formulas corresponding to that new sequence. So here I just added has preceding sibling to all of the initial formulas. So that's what I can do with formulas. So I can have richer types for my sequences. And now what about type checking? So what I need to do if I want to type check my program is to prove that, so prove using only the type of S that S/following sibling, etc., gives something which always matches the regular expression A question, B or C or D star. So I need to do a containment check between the regular expression of formulas I have computed and the regular expression of tree types, which is given by the DTD. So the way I can do that, the way we can do that is to use a satisfiability checker to compare individual node types. So I have an alphabet in my right-hand expression. It contains A, B, C, and D. And I have a certain number of formulas which appear in my regular expression of formulas. And I will first compute which ones have a non-empty intersection between these formulas on the left and the types on the right. And I also need to check whether one formula can correspond to anything else than the types A, B, C, and D. So I will do that using a satisfiability checker. And here I can compute that my first formula is compatible with B, C, and D, but not with A, and not with anything else. So I can deduce from that any node which matches that, which satisfies that formula is either a B, a C, or a D, and nothing else. And the second formula actually matches nothing on the right, because in fact this formula is not satisfiable. So if you remember the types, it's not possible from a D2 node to have, I mean, the types said that X has one child, which is Y, and Y has at most one child, so it is not possible that this grandchild has any sibling. So then from here, I can just do a standard regular expression inclusion check. So I convert every formula on the left into a disjunction of types. So the first formula is converted into B or C or D. The second formula is converted into nothing. And then I can do a regular expression inclusion check. And I can prove that this expression is well typed in this example. So to summarize what we did, so we propose a novel type language using these regular expressions of formulas, which more accurately represents the structure of values in XQuery than the classical type language, which is based on regular tree types. So we have a type system for a core of XQuery, which accepts previously untypable but correct programs. And also a feature of our system is that we use a satisfiability checker. So it's expensive, it's X time, but we do many small calls because we compare individual tree nodes. We have many small exponential calls instead of one big one. So on that example I just showed you, well, we have called the solver 12 times, but it does respond quickly. So some perspectives from here. So I have not talked about functions, but here what we can see in these examples is that we build intermediate types with formulas. So here, for S, we build a type containing formulas, but the types that are given at the beginning are still DTDs, so they are still regular tree types. But if we want to type a function, so for example, a function which takes some node and returns its parent or something, if we want to have type annotations for this function so that we can type it out of context, it would be useful to have a type language which allows expressing constraints on the parents, the siblings, etc., on the parameter type of the function. And such languages exist, so schematron is such a language, and we can translate schematron constraints into logic formulas. So it could be a possibility to extend our XQuery core with type annotated functions with schematron type annotations. Also, what I would like to add is that, okay, it is about XQuery, but it's not very specific to XQuery. So the reason why we consider XQuery is because it has a type system, but that type system has problems, but other languages could benefit from this. So navigating between siblings in the tree is a common use case. For example, in preference lists, you have systems of key values, and from one key you want to get the value which is the next sibling in the tree, etc. Also, thank you.
I just had a small question that I didn't understand. No, forward. It's when you do the parentheses. You have the angle braces and you have the square braces.
Sorry?
The slide where you introduce the angle braces and the square braces.
Oh, sorry. It's here?
Okay, yeah, no. Now they're backwards navigation. I don't understand what the 2 means for backward navigation. Does that mean my second parent?
Okay, so this means, so 2 is I am a right child. So the diamond 2 bar means I am a right child and my parent satisfies some phi.
Okay.
And the square 2 bar means if I am a right child, then my parent satisfies phi.
Okay, thank you.
Also, very minor, but just to be sure, when you give type for C, for S, sorry, before.
You mean here or?
No, before. Even before, I think. One more. Okay, no. Before.
When I give a type for C?
Yeah, for S.
For
which
S.
is defined here.
Okay, sorry. Here, the type of S is C star X question. Because here, so from D1, I take
yes,
all children named C.
Then you give a more precise type.
Mm-hmm.
Right here.
Yeah.
So this second question mark optional, should it be star instead? Because the 2 star may have many results.
Well, it's a question because of the type of D2. So D2 has this type.
I see.
So
thank you. Yes.
It can have at most one grandchild.
Thank you.